Hey, what's up guys? My name is Chono and welcome to episode 99 of Game Programming. We are really getting close to episode 100 now, and I'm running out of ideas as to what to do to celebrate that massive occasion. So leave a comment below if you guys have a wild idea. But nonetheless, episode 99, we're going to talk about nodes. Also, I've kind of changed the way that I'm recording this. I used to actually record like my entire screen and then zoom in. Now what I've done is I'm just recording a section of my screen, and that's just because sometimes I forget that I need to zoom in onto something in like post-production and I won't do it, and then like I won't show what I'm doing and mess. So I've done this way. All right, let me just empty my recycle bin real quick. So let me know if this is better or worse. I don't know. You know, I'm mixing it up for episode 99, all right? So nodes. Last time we did vectors, and nodes are going to be based on vectors essentially. So what is a node? Well, I've got this little program here, so I can move windows in the right way. And I'm just going to basically illustrate to you what our deal here is. So basically, like, if I just illustrate what we've got going on with our game right now, yeah, we've got like this, that's really not very, I'll have to press harder. I suck at this. We've got this, let's just pretend that this is our game world, right? Obviously we're using tiles, so thus we have a grid, and these are all of our different tiles that we may have in our map, in our level, right? Let's just say that this blue will be a player, okay? Player's right over here, all right? That's the player. Now this pink here, or purple as they call it, is an enemy, or rather a location that the entity wants to get to. Okay, so blue is an entity, and pink here, or purple, is the location of where the entity, that's clearly pink. I don't know why they call it purple. Maybe I'm colorblind. That's like the location that we want to get to. Okay, that is the entity. That's where we need to find the path to. Of course, we are using the A* search algorithm. If I didn't say that at the beginning, I don't think I did. But basically, to get from point A to point B here, we need to somehow figure out a path using the A* search algorithm. Now, what are nodes? Well, this is interesting. This is where it comes into play here. A node will be marked by the color red here. I'll actually just switch to a paintbrush. That might be easier. Paintbrush. Okay, that is easier. So we've got this we've got this situation here where we're going to get where we want to get from point A to point B. Now, a node is essentially, I guess, a waypoint. Think of it as a waypoint, right? And a waypoint being a location that we can technically go to, right? So if we look at our entity here, well, the world is tile-based, but we can move, you know, in pixel precision, essentially. But we definitely don't want to make every pixel a separate node because that would be awful for performance. So what we want to do is we want to break it down. Well, can I go here? Can I go there? And because we have a situation in our game engine right now going on where this is more of a in-depth kind of feel with this diagram, but I hope you guys won't mind too much. We've got this kind of situation going on where we don't have any kind of half tiles, right? So in other words, a tile can only be one type and one type only. So we can't have something like a wall that occupies half the tile. Basically, if a tile is not solid, it is a valid tile. We can be there. We can cross that tile. Obviously, if a tile is a wall, we've got a problem. And that's the main thing that we want to fight against, don't we? Tiles that we actually can't physically get across. So because every tile is all we need to know about that area, we can simply assign a node to a tile. So one node equals one tile. So in that case, all of these things, they're all nodes, right? Every tile is a node, including that one. I'm not going to put a red one there. This is also a node, by the way, this blue thing. I'm just not going to litter it with that. So all of these are potential candidates. Now, let me grab my pencil here real quick again. So, and I'll make the color green. So in order for us to get here, the A* algorithm can actually examine each of these waypoints, right? So it can say, okay, to get here in the shortest the shortest path possible, I'm probably going to go up here. Green was a bad choice. I'll just make it black. We want to go up here maybe, then maybe here, and then, well, there we go. That's a pretty short path right there. Yeah? we can go like that. It does that. Now we can't go like that. That would be ignoring the nodes. Basically, a node, of course, is an area that we can go to, okay? Now, there might be a wall here. If this is a wall, A star says, okay, well, I can't go there, right? It checks all the adjacent nodes, and we'll talk about this later. But it checks all these nodes, and it says, okay, I can't go here, but I can go here. So I'm going to work my way around here and find that as a path. But the point is, it needs these nodes because it needs to know where it can look for a path. And we're assigning a node equal to a, not to a path, equal to a tile here because that's, well, that's the best way that we can do it right now. Now, you might also notice that I've put nodes in the middle, not in the top left. And we'll probably talk about this later, but when we have a tile, the coordinate of this tile in terms of pixels, where it starts is always going to be up here because we start rendering from here and we go this way and then we basically scan it like that, don't we? But we start up here. Now for nodes, it's very, very common to want to put that origin into here for obvious reasons. But, and one of the reasons as well, because they might not be so obvious for you guys, is if a entity here, which is going to be this little smiley face, is moving across multiple tiles, we don't want him to be moving in the corners. We want him to kind of be moving through the centers of the tiles because it just looks cooler. Okay, that's another example. But essentially, each of these nodes, the way that we're going to store them, and I went over this last time, the reason we even needed vector coordinates was because of the fact that tiles don't know where they're located, right? The location of a tile is not stored in the tile. We only have static instances of tiles. A grass tile, there's just simply one instance of the grass tile. It just gets drawn multiple times. So because of that, tiles have no idea where they are. We need a system to work out where they are. So we use nodes for that. And nodes, of course, the position of a node is going to be stored as a vector to I, and that's where that comes in. So now let's switch over to our code. Hope you guys enjoyed that. I really do want to do more stuff like that with diagrams and stuff. Let me know if you guys want me to, because I think I might just make one-off videos that aren't part of any series that deal with topics like that and actually illustrate them and talk about them in depth. I really want to do that for a while. My holidays are coming. My university is finishing up for the year, so I might just do that over the break. So a node should probably belong to a level as well. Yeah, not really a utility, because a node kind of is part of a tile, and that's kind of a level thing. So I'll right click here, hit new class. You guys know the drill. And I will go ahead and call the class node. All right. And a node needs a bunch of things. The first thing a node needs, and we're going to make all these fields public, by the way. The first thing a node needs is a vector. So a node needs a location. So usually we'd go ahead and go like that, public in X and Y. We're not going to do that. We're going to go ahead and say public vector to I. All right, and we can call this location. I'm just going to call it tile. And the reason I want to call it tile is because a node is supposed to represent a tile. This will just make it a bit easier for readability. And of course, I'll import that class. We also need to make a parent node. Now this is interesting, and I'll explain this in a minute. And then we need three little calculations that A star will use, called fcost, gcost, and hcost. This is a great time to explain this thing, isn't it? Well, better make sure that's a double. Yeah, okay. So let's actually just write out the constructor first, and then I'll explain everything later. So we need to specify a tile, of course. We need to specify a parent node. We need to specify a... I didn't close that. Good, I didn't. We need to specify a... what else? Oh, well, all the costs, I guess. Except for fcost. And I'll tell you why in a minute. hcost. All right. So... we'll do the normal thing. This dot tile equals tile. This dot parent equals parent. This dot gcost equals gcost. And whoops, make sure you write it out in the same case. This dot hcost equals hcost. Right. And then that just leaves fcost. What on earth is fcost? Well, fcost is actually the combination of gcost plus hcost. So we can simply express that as this dot gcost plus this.hcost. Now you could remove the this and that would refer to the parameters, but it's probably safer to do it this way just because we might modify it outside of the function for some reason. But that is it. Okay, so first of all, let's cover the parent. What is the parent? Now the parent, you might notice, is the same type as this class, all right? So what this node class does is it has an instance of another node, okay? And the reason for that is we need some way to trace our path. So let's talk about that quickly. So hopefully, no, this should be fine. I don't think you guys will mind having all the other stuff in the way here. So we'll make blue. No, we've used blue. Yellow. No, I can't see that working out. Orange. So we've got our little entity here who wants to get to this point, and that's fine. But what happens is, as a path gets drawn, as we work out a path, we need to know where we came from, and that's where the parent comes in. So basically, the first node that we are at is the node that we are going from. It's the, I guess, the start, right? That's the finish. This is the start. Now, the start has a node, and the start's parent, right? So the start's parent is null. This is a horrible choice of color. Null. All right? It's null. So the start doesn't have a parent because it's the first one. All the other ones, though, do have a parent. So this node over here will have the parent of this node. Now, that node by itself does not automatically have the parent of this node. The reason this is the parent is because, as you can see, this is the path we choose. So in other words, if we choose to go from this node to this node, the node that we came from is this node's parent, right? And then we keep going like that. And the reason we need to store this parent is because when we get to the finish, we want to trace the path that we used to get to the finish so that we can then return that path and actually do something with it, like, for example, move an entity along that path. Now, in order to actually trace back our steps, we need each node here to know which node led to this node. So this node has to know that this node came to it, right? Not this node. This node has nothing to do with us. This is the parent. This is where we came from. And using that kind of recursion, we can actually trace back our steps to the beginning. All right, that's what the parent is used for. Now, fcost, jcost, and hcost are three calculations of costs, right? And a cost is how much, I guess, it costs to get to a path. So in other words, if we roughly look at this, is going to be a cheaper cost. A cost is almost like a distance, all right? Think of it that way. It's going to cost, this is a pretty low cost path, right? If we go all the way around here, that's going to be a higher cost, right? Because the distance is higher. Now, these three, there's a bunch of different costs here. There's a heuristic cost, there's an actual node-to-node cost, which is the G cost, and then there's the combination of them, which is called the F cost. And these three are actually used by the A-star search algorithm to figure out how it can actually find out what the fastest, what the shortest path possible is, because that is what A-star is all about, figuring out the shortest path to a, well, see, the word shortest isn't used, the word lowest cost is used, and the reason that's the case, if I just shove over here and give myself some more room, the reason we use the term lower cost instead of shortest is because, picture this scenario, we've got this area here, right? We've got, we just happen to have, I'm not going to draw tiles here, but we just happen to have a river. That's a river that ends here. Now a river's water, right? We can cross that technically if we really need to, but we've got a player here or an entity, because AI isn't typically used on player. And we've got the destination over here. Now, it would be a shorter path to go from here to here like that, right? But would it really be a lower cost? Because water might slow you down a lot. So technically it might be shorter in distance to go here, but it might be faster and thus lower cost to go like that. And A-star will actually take in this like obstruction as a possibility. It won't just simply be like, okay, that's not a wall, we can pass it, I'm going to choose this path. No. If we give it the necessary details, it will actually go ahead and say, all right, well, I can cross that technically, but, you know, maybe there's a faster way. and it will explore that, and it will find the faster way. And then it'll take into account both of these paths, and it will be like, okay, this one's better. I'm gonna go through this way. All right. That's why cost is different than, I guess, distance. Okay, that's pretty much it. All right. And F cost is simply a combination of these. G cost. Let's talk about G cost really quickly. Okay. A G cost is, I guess, it's almost like the total node to node cost. All right. Now let's. I really don't want to make a new. Hang on. Let me just quickly save this into pictures, and I'll call it. I'll just call it Cherno1, whatever. Because I like this diagram. Not that it's very neat, but I like it. All right. Hope that actually saved. So let's picture this little scenario here. I'll have to draw my grid again. I really wish there was a line tool in Autodesk Sketchbook Pro, which is what I'm using. But I don't think there is, so that's a pity. All right, so we got a bunch of these. And these are all, of course, tiles. And then we've got a bunch of nodes, which I will draw with the paintbrush because it's faster. Cherno is the best. Okay, so we've got this stuff, and we'll make this black. So we've got all these nodes, right? And let's just say we're traveling from point A to point B, yeah? As we travel, we have to work out distances, and we actually have to keep track of how long this path is taking us. Somehow we need to know, well, okay, I go this way, I'll go this way, I'll go this way, I'll go this way, I'll go this. Hang on a minute, where am I? How long is this path taking me? Okay, we need to keep track of how long it's been since the start. Now, for a very simple calculation, going this way is going to cost more than going this way, right? Because it's physically a bigger distance, right? If we look at this distance by itself as basically a triangle, as you can probably see, let's just say that's one, let's just say that's one tile. This would clearly be the square root of 2 tiles, right? This is really basic trigonometry, I guess. As long as this, of course, is a 90-degree angle, and both the height and width are both equal to the same value here. All right, and this is roughly 1.41. That's the square root of 2. So this is really basic maths. Again, an in-depth series would cover this in much more detail. But the point is, it's going to be a longer distance going this way rather than going left or right or up or down. Going diagonal is actually going to cost us more. Now, we need to keep track of this cost. So once we go, well, still, it's going to be better than going like that and like that. That's the other thing you have to consider, right? Going this way and this way is, of course, more expensive than going just this way because it's 2 directions. And that's 1 plus 1, right? Which is 2. This is the square root of 2, which is 1.41. 1.41 is, of course, lower than 2. So, of course, in this case, this would be the much preferred path. And then we can go this way again. Although I think A star might want to calculate it going this way, depending on a bunch of things. Just because that is the first occurring path, and it's cheaper. But the point is, we'll get here eventually. And one thing that we need to consider now is, okay, well, once we're up to this node, what is our total cost since the start? Yeah, let's figure out how long it's been. So that's where this comes in, and in this case, it's square root of 2. Cool. Now we go this way. Okay, well, now our distance is, of course, the square root of 2 plus 1. Yeah? And then from here onwards, our distance is again the square root of 2. Right? Pretty simple stuff. So, of course, eventually what we would get, well, a value here, but eventually what this accounts to is something called J-cost. Yeah? J-cost is the sum of all of our, I guess, node-to-node distances. Simple as that. Now, what is the H-cost? This is a big one, probably. It's bigger than this one, probably. The H-cost is actually just a direct distance to the finish. Okay? So J-cost, of course, being the sum of all of the nodes that we've been to. So our current distance from the start is our J-cost. And now we need a distance from the finish. Now, a big factor comes into this. We don't know how to get to the finish yet. That's the whole reason we're calculating this path. So we can't go ahead and say, okay, well, the J-cost at this location, let's switch to green. The J-cost at this location is root 2. But the h cost, well, clearly it's going to be 1 plus root 2. Well, no, because we don't know that we need to go this way and then this way. We don't know that. That's what we're trying to calculate. How can we know that we need to use this path to get there? Yet we don't at this point in time. So h cost isn't actually the same way as, it's not calculated the same way as j cost. It's simply it's just a direct line. It's direct like distance, like as the bird flies, distance, right? Which is just gonna look like this. Okay, it's just like that. If it was here, if it was from here, if we were on this node, the h cost would be like that. All right, and the way that we work it out, of course, is simple trigonometry again, Pythagoras theorem. It's simply going to be that squared plus that distance squared, and then all that square rooted. Okay, so essentially the start x squared plus the actually that might take a bit of time to work out because we need to subtract the finish x as well, and then square it, and then add the y, and then square it the whole thing. We'll talk about this in more detail next time. But the point is, it's just a straight line direction. And of course, f cost is simply going to be the total cost. So we've worked out both of these costs individually, great. But the cost that we're actually going to use to govern them, in other words, to actually let the algorithm tell us what the shortest path is a combination of these two, because they're both equally important. And that will be the f cost plus the g cost, which is otherwise known as the f cost, which is our total cost for the current node and for all the nodes that we explore. Now, that is some pretty in-depth stuff. I did not want to go this in-depth, and I probably won't be in the future. I'll probably save that stuff for actual in-depth videos, but that's all you need to know about g cost, h cost, and f cost, as well as the tile parents. So that's it. That's going to wrap up this episode of Game Programming. Hope you guys enjoyed it. Pretty good 99th episode. Next time, we're going to take a look at probably... What are we doing? Probably actually starting to implement this. I reckon we're pretty much ready. So we're going to actually start writing out the algorithm next time. And we might finish it probably. Actually, that'd be a great 100 finish. Yeah, we'll probably finish it next episode. Well, at least we'll finish the algorithm. We won't actually finish the entities moving to their locations, but we'll finish the algorithm, and we'll start and finish the algorithm next episode. Also, if you guys want to download these videos and watch them offline, you can certainly do that. thechurno.com/ I don't know the link because I'm an idiot, but thechurno.com/ game programming will guide you how to get there. And you can download these videos for $10. You get basically all these episodes available for download, as well as a package to download them all at once. So in other words, you don't have to individually download them. And I mean, like $10, like that's pretty cheap. That comes down to 10 cents per episode. 10 cents per episode. Okay? So if you guys really think my videos are worth that little, you can go ahead and buy that. And that, of course, will support me and enable me to continue making these videos. So thanks for watching. If you guys did like it, please hit the like button. If we can hit 300 likes, I'll make another video tomorrow. And I'll see you guys next time. Goodbye.